Have you ever witnessed a compass needle spinning wildly, almost uncontrollably? It's a perplexing sight, isn't it? Instead of reliably pointing north as it's designed to do, a compass is supposed to be a steadfast guide, a reliable indicator of direction. It's not science fiction. This can really happen in certain places, defying our expectations of how a compass should behave. Sometimes, deep underground, in the hidden depths of the Earth, huge deposits of magnetic rocks like magnetite, rich in iron and magnetic properties, create local magnetic fields so strong they confuse your compass, disrupting its normal function. You might also see this near the Earth's magnetic poles, in the far northern or southern reaches where the field lines dive straight down, creating a unique magnetic environment. But more often, it's human technology, our own creations, like high-voltage power lines stretching across the landscape or big electrical machines, powerful devices humming with energy, creating strong, changing magnetic fields that ripple through the surrounding space. That make the needle spin, a visible reaction to the invisible forces at play. A simple magnet can make a compass point in a new direction, influencing its alignment, but only a rapidly changing magnetic field makes it spin continuously, unable to settle on a direction. Alternating current and power lines, the kind that powers our homes and cities, flips the magnetic field back and forth, constantly reversing its polarity, and the compass needle tries to keep up, spinning in response to the fluctuating magnetic field. The spinning compass isn't broken, it's not malfunctioning, it's showing us invisible forces at work, revealing the presence of magnetic fields we can't see. This raises a big question, a thought-provoking inquiry into the nature of energy. If there's enough energy to spin a compass, enough force to cause continuous motion, could we harness it to power something bigger? Could we capture this energy and put it to practical use? Let's find out how this connects to generating electricity, and explore the potential of these magnetic forces. To see if we can tap into the intriguing energy of a spinning compass, and potentially harness it for something useful, we need to first understand the fundamental principles of how electricity is made in the first place. Let's delve into the science behind it. The key to this understanding lies with the groundbreaking work of Michael Faraday, who discovered that moving a magnet in close proximity to a coil of wire creates an electric current, a phenomenon that revolutionized our understanding of energy. This remarkable process is known as electromagnetic induction, and incredibly, every single power plant across the globe uses this very principle. They spin a magnet rapidly inside coils of wire, and through electromagnetic induction, you get electricity. It's that simple, yet that powerful. Hydroelectric dams, wind turbines, and even coal plants all spin turbines, which in turn rotate magnets, and ultimately generate the power that fuels our modern world. The key, the absolute essential element, is motion. Because a stationary magnet, no matter how strong, simply won't do the trick on its own. The magnetic field must change rapidly, it needs to be dynamic, sweeping across the wire to effectively push electrons along and create a usable electric current. And that's precisely why a spinning compass is such an intriguing and potentially valuable phenomenon, because it inherently means there's a dynamic magnetic field actively present. But the crucial question remains, is that field strong enough, and is it changing fast enough, to actually generate a useful and meaningful amount of electricity? The next logical step is imagining a completely new kind of power plant, strategically built on top of a naturally occurring magnetic hotspot. Could nature's own inherent magnetic weirdness, this untapped potential, ultimately be harnessed to power our entire world? It's a question worth exploring. Imagine a valley full of magnetic rock where compasses spin. Could we build a power plant there? We'd set up huge coils of wire hoping the natural, fluctuating magnetic field would induce current, just like in a generator. In theory, nature would provide the spinning magnet, and we'd just collect the electricity. But for this to work, the magnetic field must be extremely strong and change very rapidly, hundreds or thousands of times per minute. Most natural anomalies are either too weak or too slow. We'd need to find a rare, hyperactive magnetic spot, then build massive coils to capture the energy. The idea is exciting, a generator with no moving parts, powered by Earth itself. But does nature really provide the right kind of energy? Here's the catch, a fundamental principle that governs the universe. The law of conservation of energy states that energy can't be created or destroyed, it can only be converted from one form to another. So, energy can't simply come from nowhere. It has to originate from some pre-existing source. Hydroelectric dams harness the potential energy of falling water, wind turbines capture the kinetic energy of moving air. But what powers a magnetic anomaly? Where does the energy to cause such a disturbance originate? Most natural magnetic fields, like the Earth's, are static. They are relatively constant over time. They don't move or change fast enough to induce a significant electrical current or generate electricity in a practical way. Spinning compasses are usually caused by man-made sources of electromagnetic interference, like the powerful electromagnetic fields surrounding power lines, and not by some inherent energy source within the ground itself. Even rare natural electromagnetic fluctuations, like those emanating from solar storms and causing auroras, are far too weak and slow to power anything of significant scale or practical use. To generate real usable electricity, you need a powerful, consistent, and rapidly changing magnetic field, something that nature simply doesn't provide readily available at a scale we can exploit. So, even if we optimistically built a power plant directly on top of a magnetic hotspot, we'd still inevitably need to mechanically spin a magnet ourselves to induce a current, using the power of wind, the force of water, or the pressure of steam. The spinning compass is merely a symptom, an indicator, and certainly not a self-sustaining source of energy. The alluring dream of a passive, free-energy magnetic power plant, unfortunately, just doesn't align with the fundamental laws of physics and therefore doesn't work in reality. So, can a spinning compass power plant work? Not really. Not the way we hoped. The idea of passively soaking up energy from a magnetic anomaly isn't feasible. The energy just isn't there. But, the core concept, spinning a magnet to make electricity, is exactly how all our power plants work today. The spinning compass is a side effect of the generator, not the cause. Building any power plant is a huge engineering challenge, and strong magnetic fields can even cause problems for navigation and wildlife. In the end, the real challenge is finding sustainable ways to spin the magnet, not finding a magical magnetic spot. That's the heart of our quest for clean energy.